Okay, now I'm muted.
There you go.
Okay, hello everybody. Let's start our presentation. Today we have not an easy lecture. That's probably the most difficult lecture of this series. I plan to have 2 lectures more. We have totally about 10 lectures. The next lecture we'll do gravitation. And today we'll finish everything related to the electromagnetic field. Basically, in physics, we have 2 major fields, the electromagnetic one and the gravitational one. And today we'll continue about the electromagnetic field that we started the last time. What is the difference between them? The difference is between them, we know that relativity must, force has to depend also on the velocity or the forward velocity. And we have 2 types of dependence. For electromagnetic field, we assume linear dependence. And this told us that the force has to be antisymmetric 4x4 tensor, which has 6 components, which could be identified with the electric and magnetic field. While for gravitation, we will see we need to have a quadratic in this forward velocity. Now, what we have done the last time, we discussed that really, in order to consider that the field propagates with the speed of light, we must consider a different type of coordinate, which taking into consideration this idea, and we must consider fields. Why? Because we cannot say that the acceleration, that means the change in behavior of the object at time t, will depend what happened with all other things in the system at time t. Because we have to know his acceleration, we have to know where the source of the field was in the past, since it took time until this field reached me at the time t. So the whole previous approach that when you have a differential equation, knowing information about t gives you the information about t plus delta t, does not work in relativity. So partially we can overcome this problem. If we know the position of the source at any time, we solve, first of all, the problem to define the field at any point xt, and then the object interacts with the field at the same point. Then we can write the usual dynamics equation, mass times acceleration equal for the strength of the field. But how will define the field? So to do this, we have saw the last time, it's convenient to introduce bipolar coordinates, and the idea was to split the space into 2 subspaces, 2-dimensional subspaces, M0 and M1. M1 is the regular XY plane, and M0 is Z and T. And we introduce those coordinates as we saw now in the supplementary information. We introduce those bases. What I'll need for today from this basis, both bases depend only on the angles. They don't depend on the radial distances. Moreover, you have a very nice formulas for the derivatives. D naught depends only on theta, and when you differentiate by theta, you get D3. D3, when you differentiate by theta, you get D naught. When you differentiate D1, you get D2, and D2 minus D1. Yes, you have a nice formulas also for the derivatives of them. This will be very helpful when we want to do some calculus with those new angles. And the forward light cone is rho 0 equals rho 1. And in this case, any null vector is the sum of the 2 vectors. That means, what are those 2 vectors, D0 and D1? That's a unit vectors by projecting this null vector into the planes M0 m1, and both have the same length, so we can write the length outside, and you get d0 plus d1. That's what we need from the previous lecture. Now we introduce the prepotential. The prepotential was introduced as for a single source field is a complex value function psi of x in Minkowski spacetime M. That means this is an expression for the field. We'll see how to get from it the full information about the field at each point. So once more, we are talking about complex valued function. Now, how we build it. We introduced a null vector from x to the position x, basically from x tilde to x, the source of the retarded time. So you draw a backward light cone. L is the line, world line of the source. You see where the backward light cone crosses this world line. There's only one point where it can cross, and this is called the retarded position. And R is equal x minus x tilde. I want to use in this way, it's easier to work with forward light cone. So mostly we'll x tilde, or x will be Rx plus x tilde. R is basically showing you the direction where the field propagates. It started with x tilde, it propagated and reached my point x at the time t, at my time t. How we'll define the prepotential? The prepotential is defined k, which is the strength of the source, times the complex angle. We introduced a complex angle, theta, from here, and phi from here. Theta minus I phi is a complex angle corresponding to the position vector r. We will use also a continuous version of this. This is non-continuous because phi has a jump at 2 pi and 0. So if we take the exponent of it, it became a continuous. And sometimes it's used, we'll use this one. The difference is almost only how the action, but all the calculations are the same. And we use the matrix representation, represented any matrix by 2 by 2 self-adjoint matrix, when the norm is the determinant, using Pauli matrices. And we define the conjugation, which commutes with this representation. Pi L is multiplication by the Pauli matrix from left, that's left. You can have it from right also. And what was interesting that this representation keeps you psi invariant. That means this function, any observer which be transformed by use of this representation, you observe the same wave function of the field. We defined on the basis vector as here represented you, and we'll need also the transformation of the dual basis. That's what we will use. You see for the dual basis, D0 star is minus D3, D3 star is minus D0, D0 upper one is ID2, and the last. That's what we'll need from the previous lectures. Now we have to do a little bit work to learn how to work with this new coordinate, how we can differentiate things. We have this light cone, we're changing the position of the vertex. The x is the vertex of this light cone. So how this will affect the world line, how it will affect the relative position. So we want to define, first of all, the derivatives of the relative position r. So what we mean? We have this point x, and we have the relative position. We moved by delta x in some direction. So the cone moved aside. The new cone will have a new intersection point, and this blue one. And we want to find what is the difference between this new one and this one to find the derivative of this map. This trick is borrowed from electromagnetism, and hopefully we'll be able to use later also in gravitation. So here how I learned from them. You denote R with index comma mu means the partial derivative of R with respect to mu. Really, you differentiate by X. Means R is a function of X, mu, and it's the partial derivative of X with respect to the X mu. Now we'll have to introduce tau of X. Tau of X on this line, on L, you introduce a parameter, proper time. It's not the time in our system, not the time on our vectors when we fix. It's proper time on the line, which we know it is ds divided by c. So we get units of time, and that's the time if the clock would sit on the wall line of the source. So on L, x tilde, this point where we have the intersection, is what it is depending on the point x, and we denote by tau x the value of the parameter tau corresponding to this x. Now let's start to differentiate this. R is x minus x tilde, so we differentiate x by mu minus x tilde by mu. X by mu will leave. X is the same vector x1, x0, x1, x2, x3. So for instance, when we differentiate by x0, we'll get 1 in the first case, and 0 in all other places. When we differentiate by x1, we'll get 0, 1, etc. It's a delta function. How we differentiate x tilde? This point. So we look on the definition. X tilde is a function of tau, and tau is a function of x. So we differentiate by the chain rule. The x tilde by the tau, the x mu is tau with the lower index, comma mu. Now, what is the x tilde d tau? That's by the definition the forward velocity of the source at the retarded time. So we have x mu minus u tau, derivative of tau by x mu. Okay, now we use that the vector r is a null vector. That means the dot product in Minkowski space of r with itself is 0. Let's differentiate by x mu. We'll get r derivative of x by r by mu is 0. Now let's perform this differentiation. What is the dot product? The dot product is contracting the two vectors. You have to put them the upper indices for two vectors, and then contracting it with eta alpha beta, where this is the metric of Minkowski spacetime. Okay, we substitute for r mu the expression that we got on the previous line, and I put delta beta mu for this one, and minus u tau mu. Now let's look on this expression, the first expression. We have beta and beta here, and the delta function changed the beta to mu. So we have eta alpha mu r alpha. That means it picks you up the mu component of the covector r. It's r sub mu. According to the laws, this is the lowering the index. Eta alpha mu of r alpha is r with lower index. Then you can go to continue here. Here you have r alpha and u beta, and eta alpha beta is exactly the dot product of r and u, and you are left with tau derivative by mu. So that's, we use the r was a null vector, and we get another identity. You got 0 equals r mu minus this expression. That means taking on the other side, you can get an expression for tau, the derivative of tau by x mu. That's the Thus, tau of mu, very important formula, gives you the relative vector as a covector in the direction of mu divided by r dot u, where r is the relative position vector, u is the relative velocity. And we continue, substitute this tau in the expression that we had for above for r mu, we'll get x mu minus u times this expression. So we have now an expression for the derivatives of the relative position vector. This is a key formula for getting everything in the next thing. I'll repeat it in the next slide until you get used to it. Now we need introduced a new product just yesterday, because I saw otherwise all the calculations, the notations are not so getting long. So we introduced a new product. I called it diamond product. Probably maybe we'll find somebody who talked about it, then maybe it has a different notation in the literature. So here's the definition. A diamond B acting on C is the following. You take A outside and take the inner product B with C and subtract B outside, A with C. Maybe it could be expressed by some triple product. Maybe that. In R3, it is very famous. It's called the triple cross product, occurring in a lot of formulas. You see it in electrodynamics, very often occurring, and it's not surprising that in our program it's also occurring quite often, but we need it for Minkowski space. So we cannot use the cross product there, but we can use the diamond product. So what it is doing, this cross product, on C, it projects it on the plane AB. Because if you are perpendicular to the plane, both inner products are 0, you get 0. So it's a linear map. So on the orthogonal complement to the plane AB, it is 0. So it projects down into C. And what it is doing, if AB, for instance, they are perpendicular at basic vectors, so it picks up the component of the second vector and puts it on the first place, and the component of the first vector puts on the second place with a minus. That's exactly the standard way how to rotate a vector by 90 degrees. In general, it is a rotation in the plane AB by 90 degrees, and the size of rotation is the area of the parallelogram AB. In Minkowski space, we will need it for two cases. We'll need it when A and B are both spatial vectors and orthogonal and normal. In this case, AB will be a 90-degree regular rotation of the projection of C onto the plane AB. And if A is a normal time vector, time lag, and B is orthogonal to A normal spatial vector, then you'll have a similar thing. By the rotation will be a hyperbolic rotation, as you saw in the exercises. It's not a regular 90 degree, but it is 90 perpendicular. They are under the hyperbolic metric. Now, using this notation, we can go now get one of the most difficult calculations. It was how to find a gradient in the bipolar coordinates. How to find the gradient of theta and phi when we differentiate by x in all directions. Here how it works. We remember what we need. We remember that R was rho d0 plus d1, because d0 and d1 are exactly projecting down this null vector into the two dimensional planes M0 and M1. Now let's differentiate this expression by x mu. So we consider R mu. Now we differentiate this expression. So we differentiate rho by mu and times d0 and rho by mu times d1. And then we'll have rho derivative d0 by mu. Now d0, you remember, depends only on theta. So we'll differentiate d0 by theta, we get d3. And then theta differentiated by mu, we write theta derivative by mu. Now we'll have to do the same thing with d1. Rho is left. d1 depends on phi. When differentiate d1 by phi, we get d2. And then you differentiate phi by mu, you get phi dot. This is a decomposition of this vector into an orthonormal basis, d0, d1, d2, d3. So now we can get easily formulas for all those expressions. It means what is the derivative of rho by dx mu, what is the derivative of theta by x mu, and phi by x. That's what we want to get. And this is the main formulas, how to get work with this new type basis, which is fitted more for the retardation and for the relativistic approach. And here how we do it. Let's start with rho mu. How we'll get it? We'll take the dot product of this whole expression with d0. Those are, it's an orthonormal basis, so d0, d1 is 0, d0, d2 is 0, d0, d2 is 0, so those are false. d0, d0 is 1. So you'll get r mu times d0 is exactly rho, the derivative by mu. Now, r with respect to mu, we have this expression. We got it 2 slides earlier. So let's apply it. Now we have to take this expression and take it inner product with d0. As we have seen, when we take the inner product with d0, what it picks up, this is the delta function, which picks you up exactly the component mu of the dual vector. That means you have to take the dual vector d0 and the mu's component. Similar as we had done 2 slides ago. Minus, when we take the dot product, look here, those are scalars, r mu is a scalar, the inner product is a scalar. You have only one vector. So the dot product is taking the 2 vector d0 with u and the remaining term, what we had. So really we applied this formula and brought it, composed the x mu with d0, we got this term, and the other one d0 with u gives the dot product. Now we made a common denominator. So with d0 is multiplied by r dot u. I wrote that r is d0 plus d1, so I can write it in this way. d0, rho 0 I took out, d0 times u plus d1 times u minus this term d0 u, and once more r mu is the rho, and we have to make it a covector, so the indexes 0 and 1 became upper indices, and the mu's component. Now, when we'll open this thing, I'll see that the first term is exactly as the third term, and they cancel out. So what we'll get, really, we'll get only this term times this, minus this term times this one. Now, look, if we'll make mu running index, that means you'll get the whole vector d0 upper and d1. It will apply lowering the indices. I'll take it outside. And then you'll have d0, rho we took outside, we divided by rho. What we'll get here? We'll get d0 times d1 dot product with U minus D1, D0, U. That's exactly the diamond product applying to U. You remember what it was? It is D0, D1. The first D0 is a time-like vector, D1 is a space-like, perpendicular one. So it's a hyperbolic rotation of U in the plane D0, D1. That is the gradient of the rho. Now let's do similar things with the two angles, theta and phi. Let's start with theta. So we take the dot product with D3, which is exactly the unit vector in the direction of theta. And using orthogonality, it picks you up only the term rho, this one, but D3 is minus 1. So we'll get a minus side on the other side. R mu D3, negative of it is rho d theta. Once more substituting this expression. So instead of D0, now we have D3 and a minus. So we get the covector corresponding to D3, the mu's component, minus the dot product of D3 with U times R mu divided RU. We do the same thing, common denominator. Here we don't need to have cancellation. We see right away, if you take the whole gradient, all R mu, we'll get R. And to make it as it is already a covector. No, it is a covector, and I want to make it a vector. So I have to take eta outside, and then it became a vector, and you have exactly the diamond product of R with D3. Now I'm substituting R equals rho D1 plus D0 plus D1. Rho cancels out, and we get a nice formula for the gradient of theta. Gradient of theta is eta, and what you have to do, you have to take D0 plus D1, diamond product with D3 acting on U divided by RU. By the way, the expression that we have in the denominator, RU, never vanish, because R is a null vector and U is a time-like vector, and a null vector and a time-like vector cannot be orthogonal. Means you have always well-defined expression. You have also the physical meaning. What does it mean? The dot product is the same in any frame, and if you pick up the frame which is moving with the source at the retarded time, then U becomes 1, 0, 0, and R is exactly the distance in that frame from the source to the observer. Very natural object. As further you are, the effect on your angle is less. As you know that something of the same height at a different, as further it is, the effect on the angle is less. Now, what are those two things that we have in the numerator? Really, we have two rotations of 90 degrees of the projection of U, both in the plane D0, D3, and D1, D3. D3 is exactly the direction of theta. We ignore like the change of phi, and we project down in the two planes connected with our decomposition, and in each plane we have a rotation. So that's explicit formula for grad theta. We repeat the same thing for phi, and it is doing everything works the same. Only D3 gets replaced by D2, and everything is the same. So we get the gradient of phi is eta, D0 plus D1, diamond with D2, U over RU. Now remember, what was the prepotential? The prepotential was theta minus I phi. And if you want to calculate the gradient, so we'll have the gradient of theta minus the gradient I times the gradient of phi. And look, both expressions that we have are very similar. They differ only in this place. So instead of d3, you'll have d2 minus I d2. Now we are ready to get to the four potential. From the pre-potential to the four potential. So we start with the gradient. It's k times the gradient of theta minus I, the gradient of phi. What we'll get, the same expression as we get for each one of them, the diamond product of d0 plus d1. In the denominator, we have Ru. And here you have, for theta, you have d3 and minus I, from here, d2 on U. Now I want to write it explicitly because now we'll have to apply the star. Now, when you write it explicitly, I brought in the eta. How eta is raising or lowering indices, those are regular vectors. And when we make them to covectors, you have to look, this product is this is a scalar. This is on the vector part, so you have to change the vector to a covector. And so this one has to be changed to a covector. That's the gradient. You see, when you look on the gradient, you don't see any types cancellation, something getting simpler, it's two rotations, etc. Now, when we use the four potential, we're getting something much nicer. So we have to take this gradient and we have to apply to it the star. So the star of d0 is minus d3. So where we had this d3 minus I d2 is this term. So we get minus d3. When we get d1, we'll get is minus I d2, and we had the last term because it became a minus. And this one, d3, the star became minus d0, but he had a minus in front. It became plus d0, and for this you get d1. You get such expression. Now, this expression can be really significantly simplified. How? Let's look what we have here. If we'll open here, we'll have here 4 terms here, 4 terms here, we have 8 terms. But look what we have here when the indices are the same. We have d0 in the product with u, this term. Then we have d1 with u, but with a minus. Here you get d2, and d2 I and minus I is 1, and the minus here is this one. And for d3, you get this term with a minus. What is this? This is exactly the composition of the vector u by the basis. So it is u. So 4 terms on the numerator give us the 4 velocities. What are the remaining terms? The remaining terms will have here the cross term, d1, d0 here, and d0, d1. It's written down, and that's exactly the diamond of d0, d1 on u. And the remaining terms here, they have an I, and the expression by itself is d3, d2, u with a minus, and with a plus, you'll get d2, d3, as it's written here, which is the diamond of d2, d3. That means the complex part is connected with the 2 unit vectors in the direction of the angles. Okay, let's now substitute it. So you have the first term, you have k eta u of Ru. That is the famous formula for the 4 potential of retarded 4 potential Lennard-Wichert formula, which is the basis for most effects in electromagnetic. The second term, we have this one, and if you look at the previous page, this expression was exactly rho del rho over rho, or that's the same as the gradient of lambda rho. Now, this term we can throw away. Why? Because when you differentiate another time, when you take curl of a gradient, it is 0. So this term does not contribute nothing. And we have I times some complex term, complex for potential. We'll see later what is the meaning of it. But we have now the regular for potential for the real part, and we have some complex extension of it. So the real part is the linear Wiechert potential. And if we do the same thing for the continuous one, so it was an exponent of the psi, so the exponent will give the exponent, and it will get the gradient of psi with the star, it exactly gives you A. That means you'll get the same for potential, but as a multiplication of psi. In quantum mechanics, they prefer this notation because they want to consider the electromagnetic field is represented by multiplication by the four potential, while in electromagnetism they use the psi itself, not the continuous. So we have done very serious work to get from the pre-potential, we got that we obtained the right for potential. That means the pre-potential is the one which is observed in reality. Now I'll show you how you obtain now from the for potential how to obtain the field, electromagnetic field tensor, or field strength tensor. So what we'll need only the formulas for tau, mu, and r mu that we had earlier. Now we have to introduce some cross product for covectors in Minkowski space. It means it will be now, if you take two covectors, the cross product will be a two form with lower indices. So A cross B with lower indices. You remember how we get the regular cross product? We took Levitshev-Vita with A mu and B mu. And since in the three-dimensional space Levitshev-Vita had three indices, we were left with one index, and that exactly gives us the vector product. So the vector product of two vectors became a vector. But now we have four indices, and after contracting two indexes, we'll still be left with two indices, and it has to be antisymmetric. So that's the definition. We use a little bit not A mu, we reverse the sign to be more consistent with the definition of the curl, which will be alpha of this type. If you have a covector valued function, it's in each point you have omega with lower index mu or alpha of x, and we take the differentiation operator, which is a covector. You remember when we talked about tensors, we have seen that differentiation gives you a lower index. So really we have talked about this product, and we apply here, instead of A, we use like the del operator, so we'll differentiate alpha, u alpha by beta, minus u beta by alpha. This is the derivative which is used for covector valued functions, and that's the right derivative. It is well defined, also in Minkowski space, there's no problem. Now you remember we want to differentiate, now we'll differentiate only the real part of the four potential, which is an expression, it has in the numerator, it has eta times u, and in the denominator it has r dot u. So we'll have to learn how to take the curl of such thing. So here's the whole calculation. The curl of eta times mu. It is the differentiation, the alpha beta component, you take the alpha component of u, but lowering down the indexes eta, alpha, mu, mu it is u alpha with the lower index, differentiate by beta, and you subtract the beta component of u with the lower indexes times alpha. Now, how we differentiate this? Now, the eta doesn't depend on nothing, it's a constant tensor, so the derivative goes on u. U is, you can define by differentiate by the parameter tau on the light, on the wall line of the source. The u d tau is exactly the acceleration. The acceleration is the derivative of the forward velocity. And d tau d beta, and here you have the same thing. By differentiate by alpha, you have d tau. So what you will have here? You'll have here the derivative, will have a, the component mu of the acceleration, and you lower it down by eta alpha mu. That means it became a alpha. And for r beta, here you have it, you'll have r beta divided by this product. Minus, from here you'll have this one will be acceleration, mu lowering down to beta, you have the acceleration component beta, and tau alpha will give us r alpha. Now you look on this, it's exactly the cross product of eta, that means lowering down of r and a. So we have an expression how to differentiate eta u. It is a curl of eta u, has ru in the denominator, and on the top it has the cross product of eta r and eta a. Now we want to differentiate the denominator. Denominator is ru. Ru, when you differentiate in the following way. The dot product can be written r with an index above and u and the index below contracted by alpha. And when you differentiate this by mu, I differentiate it by r. And then I'm using that I can take, on the other hand, I can take u with the upper index and r with the lower index, and differentiate u by mu. R by mu, I substitute this expression. No, this one. So you'll have x mu and u alpha. It is giving you u mu, as we have done, because the delta function and lowering down the index of mu. And then you have minus, and you have now, you'll have this term, which is u r alpha. This is the vector, and u alpha will be, no, this one. U alpha with the lower index will be meet the u alpha the upper index. So we have this expression. This expression is how much? Is exactly the norm of u, which is 1. So this will disappear here. What will have at the rest? When you differentiate this, we use what we have done here. And when you differentiate by tau, which will give the acceleration, and the tau mu will give you the r mu. And so you'll have the acceleration with alpha here, and r with alpha lower linear product, and r mu from here will be left. So you have such expression for r dot u, the derivative with mu. Now you have to do the next thing. You have to calculate the gradient of this thing. Why I'm taking the gradient? This is a scalar. For a scalar, the differentiation is the gradient. How I differentiate it? As a fraction, power minus 1, so it gives you power minus 2, times the derivative of ru, which I calculated here. So get it, this term will give you u, what with the lower index, delta, with a minus because it was the power minus 1. Then this will become a plus. I put them together. We'll get r with the index. And now the denominator, we had already ru in the square, and we have another ru to get in power 3. Now we have the most complicated calculation to put everything together. F, the field, has to be the curl of this 4 potential. We are taking now only the real part, and because I told you the image, the general part, we'll see it follows from some symmetry what it should be. So you take the real part, so substitute k eta u over r u, and you need to know how to take a curl of a vector times a scalar. It is done the following. You take the scalar k1 over ru, and you take the curl on the vector part. And then when you take the second term, will be the cross product of the gradient of the scalar part with the vector. And it has to be in this way. It is a simple calculation. Write down A as a product, a vector, and a scalar, then we came up with this one. Now both terms, everything we calculated. This one is written here. Here it is, so we write it down here. Now what will be this term? The gradient is calculated here. And now I have to take cross product, k will go out with eta u. Now look, the first term is eta u in the numerator. Cross product with eta u is 0. So this doesn't contribute nothing. And those one will give eta r cross product with u. Eta u. And this one also here because this is a scalar. So we got an explicit formula for the field. This formula is very, very famous and generally very, very difficult to obtain it directly. Here, but you have here all the steps. Now let's take a look more carefully what we got. We have really here 3 terms. The first term is this one, second term this one, and the third one this. Now let's check what is the behavior of them when r goes to infinity, far away from the source. So this one, the numerator here, is of order r, and the denominator is of r squared. That means it falls as 1 over r. The second term, when you look on this one, this falls about r, but this one is r in power 3. So this term falls 1 over r squared. And the last one has twice r, and here r cubed is one small 1 over r. So we split this f into 2 components. And it's always the 2 components behave totally different. And these are called the near and radiation fields. So the tensor, electromagnetic tensor, splits into 2 pieces. And the first one is called the near field. It decreases as 1 over r squared. That means if you are very far away, you'll not be able to observe it because the other one is only 1 over r. So basically, it's only near the source. For instance, when you have antennas, this is the parasitic field which is around the base stations. It is exactly equal k, the eta r and eta u cross product divided by ru cubed. It falls as 1 over r squared. It depends only on the retarded position and the velocity. It's totally independent on the acceleration. That's the near field. And you have another field the two other terms. It's called the radiation field. It decreases as 1 over r, depends on all three things, r, u, and a. So means if you have no acceleration, there's no radiation field. The radiation field is due to the acceleration. And it has the following interesting formula. You see, in the numerator, you have r occurs both with the product with u and with a, once cross product and once dot product, and the difference. Such an interesting expression. Let's, at least to get that it is something that we recognize, let's take the charge at rest at the origin, then u is 0, 1, 0, 0, but the velocity is 0 and u has to have no 1. A retarded vector r0 is the same as the length of the position of the source with respect to the observer. And the dot product gives you r0, it's exactly the distance between the source and the observer. And what you'll get, that the field will have the components, when you have the indices law, antisymmetric tensor, which is exactly the tensor corresponding to the field r over r cubed. That's the usual formula for electric field. And obviously, when you go to another frame, you obtain the magnetic field. And it will be right because everything is Lorentz covariant and transforms exactly as the Lorentz transformation is supposed to be. You can also try to understand why it's a radiation field. This is based on one theorem. There is a theorem which is called Poynting theorem. It tells you the following. If you have a vector field, electromagnetic field, and E cross B is not 0, then there is a flow of energy of the field in direction E cross B. I wanted to represent you the proof of it, but I have not found a good proof. I think with our understanding, maybe we'll be able to produce some nice proof for it. Because really, this is the most important field. All the communication what we have is exactly because of this field, the radiation field. With putting in the antennas currents that generating acceleration for the electrons which run there, and they produce this radiation field. And this radiation field takes the electromagnetic waves and the distances, totally disconnected eventually from the source. It propagates kilometers around and catch by other antennas. Until now, we don't have a full understanding of the mechanism of how this field got disconnected. There is energy also in this field, in the nearest field, but the flow there, it is balanced. The way that goes away is the same flow that goes back. While on the radiation field, you have a flow of energy from the source. And you can calculate it, for instance, in the frame, which is moving with the source. And if the acceleration has to be always, as we showed you, perpendicular to u, that means it has to be spatial vector. You pick up, for instance, in the x direction, in this direction of the acceleration, and you calculate this vector, and you see it is always 0 except in the direction of acceleration. That means such a field will produce radiation in almost all directions. Means you have an explicit way how to calculate how this radiation is caused. My understanding of it is that what happens, you have the field propagated at the speed of light, and then the source, if it goes with the speed, with a constant velocity, the light cone remains, simply the same light cone. But when you have an acceleration, a part of the new light cone got disconnected from the other part of the light cone in the previous time. That means you left some part of the field disconnected from the source. And then it has to propagate. Now, why it has to propagate? Because it's built up from particles, zero mass. And you remember I showed you from special relativity, such particles, they must move with the speed of light. Otherwise, they stop to exist. So those photons, which are like jumped out from the light cone because the acceleration of the source, they now are free and they are the radiation field. Okay, but it has to be put more explicitly, and I'll be very glad if somebody will be able to give a good explanation. But I will be glad. A lot of people will be glad because that's a lot of people live from this radiation field, and how to build nicer antennas, and all those things are very crucial for understanding how this radiation field got we obtained. So you see how we obtain it, really using the symmetries of the original, which gives us this pre-potential, differentiating, and getting to the field. We saw that we have two types of field. One is the near field, which has no radiation, and the radiation field, which decreases only at 1/r, and it keeps the flow of energy. Now let's see a little bit more easier things. From several sources, you get a few sources, what you have to do. The electromagnetic field is the sum or an integral of the field generated by its sources. An electromagnetic field is a result of sources of the field, so you have to know how to integrate. Now, the prepotential of the field generated for a charge distributed by Qx depends on what? The field now depends only on where the relative position of the charges on the path light cone. So really, all the rest don't give us nothing, information about the field. So we have to integrate only by the path light cone of the prepotential times this is the prepotential. You have the distribution on x minus r, where r is the null vector, which is rho, cos, sinh, etc. And times dv, the unit volume. You calculate the volume, and you see on this light cone in this new coordinate, and the plane xy, the volume is rho, the area is rho square, rho d phi, and in the theta plane it picks up cos theta. So this is the integral. So you have to integrate theta minus I phi, q on the retarded position. Look, something interesting is the prepotential, once more, is not dependent on the distance. You only have to check how much charges in each ray, theta and phi, the total charge integrated, and phi goes from 0 till 2 pi, theta goes from minus infinity to infinity, and rho, that's a mistake. Rho has to go from 0 to infinity. Rho has to go from 0 to infinity because you have to go on the past light cone, which rho was really in the positive one. Rho has to go from 0 to infinity. 11. Okay, I'll change later. But we have an explicit formula for the prepotential of any distribution. And since all the operations that we have done were linear, so you can do everything for the potential. You'll get the same kind of integral of them. Instead of k, you put this q, and you put here the four potential. You get the four potential of several sources. The same thing you get for the field tensor. Now that will be not obvious the decomposition into, no, it will also be, the composition will be also into the near and the far field will be also simple because each component has types going as 1 over r or 1 over r squared, and you combine all terms 1 over r, you get the near field, 1 over no, the radiation field, and 1 over r squared, the near field. So that's how to go from one source to several sources. Now I'm going to give you all Maxwell equations in one slide. And this is after you understand what really Maxwell equations mean, then it is quite simple to explain in one slide. Here's the slide. Let's start from this side. We started with a field which has some sources. Sources of electric field are called currents. What is a current? Current means it is a charge and having some velocity. At each point of the field, of the source, you have a distribution of charges, and nearby they're moving about in the same direction, so they have a four velocity. This gives you a four-vector field at each point. Those are the sources of the field. What is Maxwell equations? Maxwell equations based on this information, how to find the field. You want to find the field. Here, how we slowly explain all the pieces of this diagram. We start from here. If you take this field and differentiate it, the differentiation of any field, vector field, is like divergence operator. You differentiate J0 by the x0 plus the J1 by x1, etc., using also the metric. This is exactly conservation. It is 0 because charges are not generated. That's a fact. The charges can move from point to point, but you cannot generate a charge from nothing. So there is a conservation of charges. That means that if you differentiate this vector valued function, you get 0. Now, it is always a theorem if your space is simply connected. If your differentiation gives you 0, that means this J itself is a derivative of something. That this J is a derivative of something. What can be of derivative of what? It has to be a two form with upper indices, and derivative is contracting it. When you have an upper index, you're always contracting it. That's the differentiation. You'll get, contracting this will give you an 4 by 4, rank 2, antisymmetric tensor, which is called field excitation. Field excitation is the field that would be generated by the source of the field if there would be vacuum around. No vacuum, that would be the whole field. Now, in general, you want to consider fields when there is media around. So we want to do the following. When there is media around, we have what is called constitutive relation, which connects the strength of the field and the excitation. Here we want to put the F, that is the strength of the field. This tensor defines me, when I put there a charge, what will be its acceleration. F on U will be define me the acceleration. Now, what kind of field will feel the charge? You will not feel only H, because there is media around. And the media around has charges. Any material is built up of charges. Now we are talking non-conducting media. When there is conducting media, there's no Maxwell equation. It's totally different story. Non-conducting media means that the charges are not free. They cannot run away. They cannot generate current. But what they can do, any molecule can, when you have a field, it can be polarized. That means the field can move the charges, the positive to one side and the negative to the other side. Or if there are current rotation, the field can change the direction of rotation and generate magnetization. So there are two things, magnetization and polarization of the surrounding matter. This is proportional to the excitation. Excitation generates them as the excitation field is stronger, also the polarization in magnetization is stronger. So you have some kind of linear connection between this field and the new field. And F is basically a combination of those, the field original from the source and generated by the polarization and magnetization, how they act on the charge. This will be given by a tensor. It has to connect the upper indices to the lower, so it has to have 4 indices, very large tensor. Tensor 4 indices, 4 times, and each one is 4. 4 times 4 times 4, and very large. But some of them are symmetries.
256.
What?
256.
Yes, 256. But you have to reduce a little bit. Alpha and beta are antisymmetric, so it reduces. Eta and mu as antisymmetric. Mu and nu are antisymmetric. It reduces also. But still, you are left with a quite big amount. Then usually you put some additional symmetries, and you can reduce it in some cases even to 2 numbers. Permeability and permittivity of the material. But there is a tensor. This tensor can be found experimentally. Why? You can start J changing, and you can measure what is F, and then you can find the connection. That's what the engineers are doing to find this tensor. So for each material, you have this tensor. Now the acceleration, as we said, is m times the acceleration is equal to q times f on u. That means only f is the definition of the field. And when you apply to u, we get the usual, what we call Lorentz force. If you express it in the electric and the magnetic field, it will be the q times the electric field plus q times v cross product with v. So you get this F is the field, and we have seen in the earlier slides, it has the 2 components, etc. Now there are 2 more. You know, we have 4 Maxwell's equations. The other 2 Maxwell's equations are assuming that we differentiate this one in an appropriate way, how you have to differentiate a 2 form with 2 low indices. You'll get 0. Why? You want to have that this field will have a potential. It will be itself a derivative of the 4 potential. And that's exactly the homogeneous Maxwell equation are telling you that this tensor field has a potential. There exists a 4 potential such that the curl of it is F, and that's what we have done in the previous slide. We calculated this curl, and we got it. Now, in our approach, we continue this further. We went down a few steps more. We found there is a pre-potential, and you take the gradient of it and conjugation, you get the complex pre-potential, 4 potential. The real part was continuing here, but it has also a complex part. What is interesting, what will be now, how we'll get the equation for psi based on the sources. what is the Maxwell equation using our terminology. You simply substitute all the things, and you came up with a nice formula. Here's the Maxwell equation. There's only one equation, but it is of order 3. Going from here to here, you have second order equation because you have differentiation here. Here, this is not differentiation, this is multiplication. And you have a differentiation here, and you get the usual D'Alembertian. D'Alembertian is a box operator, which is the second derivative of psi by dt squared minus the second derivative by x squared minus the second derivative by y squared minus the second derivative by z squared. This is the Lambertian, and in general, the Maxwell equation in terms of the four potentials could be brought to the form the Lambertian of A equals J. And that's the way mostly in electromagnetism they solve Maxwell equations, going to the four potential and then calculating the curl of it, getting the field. Now, why I think this has an advantage? It is what we would like to give meaning for psi as a field of a particle. To be a field of a particle, you must be what is called a soliton. Soliton is a solution that far from, it has some kind of center, and from the center it gets close to zero. It means there's no field far away. It is known if you start with differential equation of order 2, there's no solitonic solutions. But for equation of order 3, there are solitonic solutions. So such equation, since it's of order 3, it may have solitonic solution. And somebody will find it, that will be very important because this will give an explicit form how to describe the fields of particles. Probably there'll be not too many. There'll be probably a classification of them. And those can be very big progress in understanding at all what quantum mechanics is about. And people try to give the meaning for psi as a description of the field, but without having the prepotential, there was no good model for it. Now this equation looks a little bit difficult as mathematically third order differential equation. Mostly they are very complicated, but this one has a very nice splitting into very known equations. Look, if you look at the Lambertian, it gives you a scalar. The Lambertian of start with a scalar and you got a scalar. Denote the expression of the Lambertian of psi of x, phi of x. So what is this expression? Is the gradient of phi with the star is j. The star I can put on j. So you have a vector field. You know that this vector field has a potential, and phi is exactly the potential. This is a very easy equation. We know how to find for a conservative field the potential, the explicit formula. You found phi, then you have also a known formula how to solve the Lambertian equals some given function. That's Poisson type equation. So we really, even though that our equation is of a third order, it can be turned in a pair of equations. This one has an easy solution, and this one is a little bit more complicated, but still solvable. So we saw that using this prepotential gives us also much nicer Maxwell equations, only one equation, and this equation has chances also for solitonic solution. And I think that's the last slide. Now I want to give you a little bit understanding the meaning of the complexification. It was a little bit strange for the electromagnetic field. We really use only the real part. What happens with the complex part? So in electromagnetic, they used a long time complexification, and it looked for them artificial tools to help solve problems. For instance, one of the first one was introducing a vector, E plus IB. Why you want to have the I here? If you want to have the electromagnetic field in one quantity, that's the only way how to describe it. Because you cannot add E with B. Has no meaning. Because E is a real vector. It has a direction. The direction of B depends on the convention, the right hand or the left hand, which is not a part of reality. That's how we decided to choose when you do the right hand law for the vector product or the left hand. So in order to be able to combine them, you have to multiply B by something which will change its sign, changing orientation. And I is exactly the symbol that we introduce when we complexify. When we change orientation, we have to change the sign of I. So we got formally such a vector, E plus IB. What was surprising, we can take the square of this vector. The square of this vector will have two parts. It will be E squared minus B squared. And the imaginary part will be the dot product E with B. And those are the two invariants for the Lorentz transformation. That means if you want to understand something obtained quantities which are Lorentz invariant, E by itself is not invariant. B by itself is not invariant. The sum of squares is not invariant. But the difference of squares is invariant, and the dot product is invariant, which is exactly the square of this vector F, the complex vector. Another reason for complexification is we explain how the field acts on a charge. But I want to remind you, what are the typical charges? An electron, a positron. But those charges are not only charges, they have a magnetic field. They have what's called spin. We describe some kind of rotation. We didn't take care of this. That means our description is missing some kind of information, how it interacts with the spin. For instance, we have two fields, and you put in spin particles, once with the spin up and the other with the spin down, the trajectories will be different, acceleration will be different. That means our description is missing. The real description is something missing, the description how it interacts with the spin. What is the thing that we got in our complex potential? It is connected with this notion of Hodge dual. The Hodge dual is a very interesting operation of antisymmetric tensor. The Hodge dual of tensor E in coordinates mu ni, you have to contract the Levi-Civita with alpha beta on top and mu ni and below. You'll get only a tensor with. It means you send each typical tensor to the complementary. For instance, this is the same, exchanging the electric and magnetic fields. This H, if applied twice, you'll not get 1, you'll get -1. So it is not a symmetry, but to make it a symmetry, you introduce, it's known that Maxwell equations are symmetric under the Hodge dual. That was one of the surprising things. We got set of 4 equations originally, and then it was recognized there's an additional symmetry connected with the Hodge dual. Then can introduce a helicity operator, multiplying this H by I, and this became a symmetry. So you have now on the space of antisymmetric tensors also a symmetry lambda, but they have to be complex in order to. Then you can consider that unsymmetric tensors of rank 2 is self-dual if lambda preserves the tensor, and anti-self-dual if it gives it to the negative. So somehow this property was lately came up that it is needed. In quantum field theory, they are imposing it as an additional property in order to be able to get any solutions. Otherwise, there are divergence and you get infinity. What turned out, if we have it's a not easy theorem, you can find it in the paper which is quoted on the first page, that the complex for tensor that is obtained by differentiate curl of the complex pre-potential. That means we calculate the real part and you add now the complex part, then F is anti-self-dual. That means this is the extension of the real part to become self-dual. Very straightforward keeping. We had something which on the regular acceleration give you the right formula for the electromagnetic field, but there is a symmetry around, and this F was not symmetric, and making it complex, it became anti-self-dual. If you want to have it self-dual, you have to pick up the right representation, then it will be self-dual. So depending on the representation, but it is a definite duality with respect to the helicity operator.
Thank you very much.
Thank you for the talk and the presentation.
Okay, bye-bye, everybody.
Bye-bye.
Thank you.